Let's do our quandary, which, by the way, our quandary leapfrogs into the lesson of the day. People often ask me why I'm such a gifted teacher, and I just don't know. I just don't know where this comes from. It's just, okay. So the first one is we've got a proton and its magnetic field. Let's say that the magnetic field is out of the page. Why is it always out of the page? Because if it's into the page, I've got to draw freaking little X's all over, right? And that takes longer, right? With dots, I can just go out of the page, yeah? Okay? So there we go, right? So let's say that this proton is moving this way. Okay, it just happens to be moving this way, and it's going 250 meters per second, right? And it's a proton, so it's got a certain mass, certain charge, right? Okay, mass is 1.673 times 10 to the 27th minus 27th kilograms. Oh my God, it was bigger than the Earth for a while there. Okay, and then its velocity is 250 meters per second, right? Which I've already written down, apparently, right? Okay, and it's got a radius of 6 meters. The first question is, gentlemen, the first question is, which way is it going to go? Let's see, it's going clockwise, right? So it's going. Okay, so which way is the force on it in this case? Yeah, the force is definitely this way, right? The magnetic force is definitely that way on the thing, right, for it to go clockwise in this field, right? And what is the magnetic field causing this motion? Well, it has to be out of the page, because out of the page is the only way that works on this, right? So velocity is this way, magnetic field's out of the page, force would be down, it's going to go clockwise, okay? And then the magnitude of the magnetic field that would cause this, what we do is we say that QVB equals MA equals MV squared over R. So here's the abstraction, right, is that we take, gentlemen, we take QVB, which is the force on a charged particle, set that equal to M times A, which is, of course, MV squared over R, right? And then we can cancel one of the velocities. And then what B are we solving for? The B. There we go, yeah. There we have it, right? So B is MV over RQ, is that right? Okay, and I think it's always better when you're typing in very large numbers or very small numbers, hard to type in numbers, right? To solve it algebraically first and then just type in the numbers. So this is 1.673, right? Velocity is 250, not a terribly difficult number, right? The radius is 6 meters, and the Q is 1.602. Yeah? It's in octal. Okay. Somebody left this calculator in octal. I don't know how to. Okay. You guys get 4.35. Yeah? Is that what we get? Are we good? Yes. Okay. Now, shh, guys. So the next thing is, and this is the segue, okay, this is an important thing, right? And that's the concept of a crossed field, okay? Here is a magnetic field coming out of the page, okay? If we take an electric field and put it at right angles to that, that's the crossed field thing, it is possible to make this guy go straight. Now, there are 3 steps to figuring out the direction of the electric field that will make it go straight. The first step is to figure out which way the magnetic force is. Which way is the magnetic force? Magnetic force is down, so we did that with index finger, magnetic field, thumb is down, right? And it's a positive charge, so the force really is down, yes? Are we good? So that's step 1. Step 1 is find the direction of the magnetic field. The second step, and this is a very easy step, is which way do we need to exert a force to make it go straight? Up. Yes, there we go. That's good. That's called, it's the opposite of down. Okay, so this has got to be the electric force has got to be up, yes? Now, the third step is which way does the electric field need to be to exert an upward force on a proton? Don't think too hard. Electric fields exert a force on positive charge in their direction, yes? So to exert an upward force on a positive charge, up the page force, right? Has to be up the page, yes? Okay, so in this case, we would, and I'll draw this in blue, we'd actually want to stick parallel plates, metal plates like this, right? We want an electric field that's this way. That means this side is the positive side of the plates, and this side is the negative side. Yeah?
Wait,
yeah.
Doesn't the proton continue to go in a circle though? So you would be like, so depending on where the proton was?
As long as it's going to the right and the field is up, it's going to go straight. Isn't that crazy? Any other angle, yeah, it's going to be all messed up.
Assuming that it's going right, though.
Yeah. Yeah, let's assume that it's going to the right.
So do you always assume that it goes right? Or do you
Yeah, you would have to answer this question. You'd have to answer this question knowing which way it's going. Right?
You
Yeah.
just assume that.
Yeah. Yeah, I'll show you another example. I think it'll be clear then. Okay, so let's do that again. Let's do that again because the direction is the hardest part. And there's basically 3 places to make a mistake, right? Okay, so let's, so remember, if you make one mistake, that's bad because you're going to get the wrong direction. So always make 2 mistakes. If you make 3, then you'll be wrong again, right? So then make another mistake, like use your left hand, for example, and then you'll be right again, okay? So the process is, they give you a picture like this. You have to know which way it's going, right? Okay? And so the first thing is which way is the magnetic force. That's what we've learned, what we're going to do a skill set on today. Velocity is this way, magnetic field's out of the page. The force is down the page, which would cause it to go in a circle, but we don't want it to go in a circle, right? So we exert a force. If the magnetic force is down the page, the force that will make it go straight is up the page, right? That's step 2, right? The third step is, what direction does the electric field need to be to exert a force up the page on a positive charge? And the answer is up the page. Why is that? Because that's what electric field is. It's a field that exerts a force on a charge, yes? Yeah? Now, velocity. Yeah. Okay, now, let's solve for the electric field, what the electric field's got to be. And this is actually really pretty simple. And then I'll show you something that's really kind of cool. And it will either help you understand it or it will, maybe on the other side, make it more difficult, if you're confused, right? So to set the thing, to figure out to set the magnetic force equal to the electric force, what we do is we say force is QVB, right? Force is equal to E times Q. So this is an electric force, right? Is E times Q. Magnetic force is QVB. Obviously, if they're going to be equal, we just set them equal, right? So we say QVB equals EQ. Now, what cancels? That's interesting, isn't it? Okay. The charge cancels. Does the mass, by the way, is the mass affected? Does the mass affect this at all? No, it affects the radius of this circle, right? So if you don't have the electric field making it go straight, the bigger the mass, the bigger the radius because it's got more inertia, right? It's harder to turn. But as far as making it go straight, the mass doesn't matter, which is kind of cool, right? The charge also doesn't matter, but that you have charge does matter. A neutron cannot be curved with a magnetic field, and it cannot be deflected by an electric field, okay? So that it has charge is important, but what the charge is, positive or negative, +1, +2, +3, +5, okay? That doesn't matter, okay? And then to solve for the electric field, well, it's just V times B, right? So we just go 250 times 4.35133 times 10 to the -7th. And that is 1.0878 times 10 to the -4th newtons per coulomb. So somehow a meter per second times a Tesla is a Newton per coulomb. That's a tag extension for you talented and gifted people. Figure out those units, right? Somehow it's got to be the same thing, right? Okay. So here is our electric field, not with the proper sig figs, that would make this thing go straight. Okay. Let's have you guys try